you for the introduction, and thanks to the organizers, Ahmed and Fabrice, for the invitation. I want to talk about positive characteristic analogs of the Thom-Sebastiani theorem. But before I get to that, let me just recall the classical story of the complex numbers. Let f a germ of a holomorphic function at 0, having 0 as an isolated critical point, and value 0 at 0. In this situation, if you consider a small ball B around 0 in Cm+1, then the inverse image of the small disk around 0 is a topological vibration outside 0 with typical fiber MF minus 1 of T, say, intersection B, which is known by Milner to be to have the homotopy type of the bouquet of spheres of dimension M in number equal to mu, the so-called Milner number, which is the dimension of C of x0, xm, divided by the ideal generated by the partials. So, if you consider the reduced cohomology of this Milner fiber with coefficient in Z, well, reduced cohomology means co-kernel of the HQ of a point to HQ. This is 0 for Q different from M, and it is Z to the mu for Q equal to M. This, in Grothendieck's notation, is, and also in Takeshi's notation, is RQ phi for this map F and a coefficient Z at 0. Now, a positive generator of the fundamental group of the punctured disk acts by an automorphism T on this group. It's called the monodromy operator, and this monodromy operator is quasi-unipotent, as was conjectured by Milner and proved by Grothendieck soon afterwards. Now, suppose that G is a second germ of holomorphic functions, say Cn+1 0 to C0, having also 0 as an isolated critical point. Then you can consider the so-called sum map F plus G from C m plus n plus 2 to C0, defined by F plus G of xy is f of x plus g of y. And it is immediate to see that this f plus g also has 0 as an isolated critical point. And also, on Milner's formula, mu f equals this quotient, you see that mu f plus g is mu f times mu g. Now, what Thom and Sebastiani proved in 1970 is the following theorem. There exists an isomorphism. Construct an isomorphism from our m phi f z tensor R n phi g of z to the similar group here R m plus n plus 1 phi f plus g of z. In particular, this formula gives that the rank here is a product of the ranks, and compatible with the monodromy operators, in the sense that Tf tensor Tg corresponds to Tf plus g. Their proof was topological, using the fact that the Milnor fiber for f plus g is a join of the Milnor fibers for f and g. So this is the story of the C. And now I want to pass to the story of a field K, characteristic P. I'm mainly interested in the case where P is positive, but you can have P equal to 0. And for simplicity, at the beginning, assume that K is algebraically closed. Now, suppose you have two polynomials, fi, or I equal 1, 2, from A and I plus 1, K to A1, K, and assume that, again, fi as 0 as an isolated critical point, or isolated point of non-smoothness. Then take n equal to n1 plus n2. Then you can again consider f1 plus f2, which can be obtained by first taking the product over k, to a1k cross k1k, and then so this is f1 the k f2, and then A is a sum map which sends xy to A of xy x plus y, and the previous f1 plus f2 is the composition AF. So then again you have a critical point for this sum map, and the question is to compare vanishing cycles for f1, f2, and the sum map. So vanishing cycles, I mean I have to vanishing cycles in the étale sense. So I have to fix some coefficient ring, lambda. So here, I will not take a finite field of characteristic L. I will just take, let's say, Z model Nu. Possibly you could take ZL, or you could take, of course, QL. You could take QL bar. You could take something intermediate here, some finite extension of QL, or you could take the ring of integers of the extension. But I'm mostly interested in the case of the finite coefficient like this. So if you consider R phi Fi of lambda, and you shifted my Ni, then this is my Gabor, this is a perverse sheaf. And because 0 is an isolated critical point, it is near 0, it is concentrated at 0. So it's a perverse sheaf which is concentrated at a point. So it has to be also in degree concentrated in degree 0, which means that R phi itself is concentrated in degree minus I. So you had RQ phi of Fi of lambda is 0 for Q different from Ni, and some power of lambda, let's say lambda Ri for Q equal to Ni. So now the question is, and of course the same is true for the sum map AF or Q phi AF of lambda, because again 0 is an isolated critical point. There's 0 for Q 0 and say lambda to the R for Q equal n plus 1. So the question is, can one find an isomorphism the form of Q phi Fi of lambda at 0, tensor here Ni phi Fi at 0, tensor R, sorry, N1, N2 phi F2, 2 R phi AF at 0, which would have certain naturality in the sense that if you assume that your situation over K comes by extension of scalar from situation over subfield K0 of K, then this isomorphism should be compatible with the automorphism of K over K0. Well, the answer in general is no. There are two kinds of obstructions or problems, if you like. Two kinds of obstructions. So no in general, I mean. In certain cases it would be possible. So the first obstruction is wide ramification. So in fact, with Takeshi, we have just seen that. In fact, in this case, contrary to what happens in other complex numbers, the Miller number for Fi, which is defined similarly as before, is in general larger than Ri, and strict inequality is possible. In fact, as Takeshi recalled, we have the Deligne formula, which says that mu Fi is not the dimension of phi and I, but the total dimension. The total dimension of R and I. Phi lambda at 0, that is Ri plus Si, where Si is the Swan conductor. And again, we have mu for AF is mu F1 times mu F2. But this translates into the formula R1 plus S1 times R2 plus S2 is Rs, and not R1 plus R plus S, sorry, but not R1, R2 equal R. Second obstruction is that even in the best case you could dream of, same ramification, both for Fi, F2, and some map, then you can't have something natural with respect to Galois automorphisms. Where is the... Yeah. So perhaps I should... then I will... Yeah. So even in the rather simple example, following simple example, so suppose you take N1, N2 is 1, and you take F1 is F2 from A1 to A1. F1 of x is x, Fi of x is x squared.
N1 plus 1 from A2, maybe 0.
And 1 equals 0.
The notation is Cn plus 12. It's An.
Oh, yes. N1 equals N2 equals 0. Yes. Yes, sorry, thank you. So then, in this case, F1 plus F2, this AF, from A2 to A1, is just x1, x2 goes to x1 square plus x2 square. And then in this case, suppose, in fact, instead of working over K, I start over just Fp. Then in this case, the R phi, in fact, concentrated in degree 0, because relative dimension is 0, for Fi is just lambda twisted by some Thymly ramified character chi of the Galois group, which is defined by chi of sigma is the sigma of square root of t divided by square root of t, so value in plus and minus 1, Thymly ramified, while you get R1 phi for AF. Well, you get the inertia, in fact, acts trivially, but you get something arithmetically non-constant. You get lambda of -1. So here this state twist. Tensor some other unramified character epsilon, which comes from, which is a character of Galois of Fp bar over Fp, and which sends the Frobenius Fp to -1p. This is seen because you want to write x1 square plus x2 square as a product, then you have to extract the root of -1. So then if you take a tensor product, then this kills that, so you get just lambda, while here you have something non-trivial arithmetically. So in 1981, Deligne proposed a solution that you should replace a tensor product by a local convolution product. So consider the initialization of A1, so maybe H, initialization of A1 at 0, and you have the close point 0 and generic point eta, and inclusion J. So suppose Mi for I equal 1, 2 is a sheaf of lambda module over eta, free of finite type, say. So this corresponds to a representation of Galois of eta bar over eta into free module, finite type. Then you can consider the product here over K and take again its initialization. I will denote it by A2H. And the sum map, or the map which is induced by the sum to AH. Now you can extend M1 and M2 by 0 onto AH, and then you can take their external tensor product over the product and localize it here, and then you apply R phi A at 0, so that you get something in a priori dvc of AH and lambda. And in fact, it turns out that our Q phi A of J lower Schrick M1 tensor J lower Schrick M2.
So this is not on. This is just on the close point of AH because it's the R phi.
Oh yes, 0. Yes, sorry. Thank you. Then this is 0 for Q different from 1. And this is something in dimension 1, which I will denote by M1 star 1 M2. This convolution was introduced first by Deling and then widely studied by Laumon in his paper on Fourier transform and product formula for the constants. And in Laumon's notation, it was a star. But later, I want to take complexes, M1 and M2, constructible complexes, and I want to take R phi or R psi, and I will use a star. So then I will here use this notation. So in any case, the Link formula was that in fact, if you replace tensor product by disk convolution, then this is correct. Then N1 phi F1 lambda at 0, star 1, N2 phi F2 lambda 0 is isomorphic to R n plus 1 phi EF lambda at 0. He gave a proof in 1981 in his seminar. I got some notes, but he went very fast, and my notes were not so good. I could never reconstruct the argument. It was a complicated compactification and deformation argument. And when I asked him recently, he said that he didn't remember. So in any case, before I say more about that, let me say the difference between star and tensor. So we'll see later that in the case K is algebraically closed, let's say, and ramification is tame, then star is isomorphic to star is isomorphic to tensor product, actually. But in general, not. And this star actually takes care of the arithmetic input I explained here. In fact, in the early 2000s, Foulet thought about the problem and gave a proof of the Deling's formula, even in a slightly more general situation, using Fourier transform, local Fourier transform of Laumon, which had the miraculous property of transforming convolution into tensor product, plus Gaber's formula for R psi, tensor R psi. So what do I mean by that? Is that Gaber had proven that formation of the nearby cycles is compatible with external product over a tray. So product something like this, here a tray. He put it in an archive, which should appear soon. I put it, I think, 2 years ago. But about the same time, maybe in 2011 or 12, Deling proposed some generalization of this formula. Which involves complexes and more general spaces than affine space. So suppose you have x1 over, let's say, AH, so Fi. So this is a finite type. And suppose you have complex Ki in dCTF of lambda. If lambda is ZL, then you could just put dBc, like in Takeshi's lecture. if lambda is FL. Yeah? Then you can consider suppose you have some point here, geometric point xi, like this, over 0 here. Then the Lie conjecture let's say D. Assume that Ki, or assume Fi Ki is universally locally acyclic outside Xi. Then you have a natural isomorphism, R phi F1 K1. So this means the right version of this star 1 previously. So it means that you extend by 0. So this is at x1. You extend by 0, take tensor product, external tensor product, and push down by the sum map, but in the derived sense. So pushing down by the sum map, you have here this A2H over AH. Correspond to taking R psi A at the point 0, but since you work with R phi, which are 0 at 0, then taking R psi or R phi is 0, so you can just take the previous formula with R phi, and you get this, and then this should be isomorphic to R psi to R phi for this map AF, defined as before, so x1 cross x2, then you have f1 times f2 to a1, a cross a1, to ah cross. And then you, you extend it to, you pull back by a2h, and then compose with the sum map. So here, external tensor product, I mean external tensor product here, and then I take and pull back here by a 2h here, and then I push by a.
So do you need to take a fiber at x1 and x2?
Yes, thank you. And here x is x1, x2.
Why did you put R phi at phi AF? What did you write there in the subscript?
Well, you take the you push that by R phi for this addition map from the A2H. So you see.
Just call it F. You don't have F. F is F1, F2.
I'm sorry. No, that's okay. Yes, yes, yes. So F is F1 cross F2. Yeah. Maybe I should write it here. So is it clear or not?
Yeah,
it's clear. So you take the product and then you apply sum, so you get the sum map. So this is so this AF is somehow the F1 plus F2. Yeah? So my result is that D is true. And in fact, this assumption is superfluous. Well, the proof is a bit stupid. I just retain from Foulay's proof the fact that R psi commutes with external products. But here, when you say that, you are a little vague. So R psi commutes with external products over a tray. But here, it's not a product over a tray that we are performing. So here, x1 over a1, x2 over a2, x2 over a1, and you perform the product over a1 cross a1. So this is a two-dimensional basis. So in fact, you would need a two-dimensional base. It would be, what you need actually is a compatibility of R psi with external products, but in a slightly more general form, like here. But then you are in trouble because you land into an unknown territory, so nearby cycles over a base of dimension 2. So, but then you have this marvelous formalism that Takeshi mentioned, the Lie, nearby cycles over general base. And then you can apply that, and you can expect a Q-ness formula, and then everything should come out. And this is indeed the case. But I will say a few more, a little more about that. So three short review of nearby cycles, other general basis. This is a construction of the Lie, 1981, I think. If you have two morphisms of schemes, say x to f and g to y, then you can construct what is called the oriented product of x and y over S. Which is not a scheme, but a topos, so category of sheaves on some site, with two maps, P1 and P2, projection to x and y. And, well, between morphisms of toposes, you can have maps. And so here you have a two-map tau from GP2 to FP1. So it's morphism from G lower star P2 star to F lower star P1 star, which is universal in the obvious sense. That means that anytime you have the topos T and projection Q1, Q2, and the map T from GQ2 to FP1, then there exists a unique map H making the two upper triangles commute, and such that T is obtained by composition with H from tau. The topos is constructed as sheaves over a site consisting of triples U, D, W, where U is étal over X, D is étal over Y, and W is étal over, S, Y, like this, with a certain topology I have no time to recall now. A point, by the universal property, what is the point of this topos? Then you take T to be punctual topos, so then you get a point of X, a point of Y, and a map from the image from G by G from the point of Y, so points of this oriented product of the triples, a point X of X, a point Y of Y, so I mean geometric point, and a map between points, that is a specialization map, like in Takeshi's lecture, from G of Y to F of X. There are two special instances of this oriented product which are of interest. The first one, which is the main object into consideration here, the vanishing topos, where you take Y to be S and G is the identity, vanishing topos. And another one is S cross S Y, the co-vanishing topos. So this was, in fact, appeared first in some work of Faltings, and later was studied by Abbes and Gros in their work on Simpson's correspondence. But I will mostly interested in this. Actually, to get a feeling about this, suppose X is just a point. Then X cross, say S cross SS, so S here, the geometric point. So this is just the strict localization of S at S. And now if you have the geometric point X of X, with image S, then the map here corresponds to the map induced by F of the strict localizations. Now, here in the vanishing topos, we have those two projections on S, and here X, P1, P2, and here it's F. So if I look here at the following diagram, so this is commutative, so by a universal property, this defines a map psi F, which in fact gives rise to a derived functor, nearby cycle functor, R psi F, from d plus of x lambda to d plus of x cross s s lambda. In the case S is a tray with close point S and eta, then this XS cross S eta is the familiar topos in the SGA 713, consisting of sheaves on the special fiber together with an action of the Galois group of eta bar over eta compatible with this action on the XS. And in fact, in this case, it's easily seen that our psi f of k restricted to this S eta is the classical, the usual R psi. And similarly, we have also some R phi, because this triangle here gives rise to a map from P1 upper star k to R psi fk, and a cone R phi k. And again, the R phi k restricted to this is the usual R phi. Now, not much time. How is this object good or bad? Then you have a notion of finiteness on this topos. I mean, given a sheaf of lambda modules on this oriented, on this vanishing topos, then you can say when it is constructible. So if F is a sheaf on lambda modules on this oriented product, you have a notion of constructible. So you have can write X as a disjoint union of X alpha and S of S beta, so that this is restriction is least. And this is a good notion. It's a thick subcategory of the category of lambda modules, and then it gives rise to a good derived category DBC of this.
You mean this locally constant, finite locally constant, not just least constructible?
Least constructible, yes. Yes, yes, thank you. Now,
equivalent to the general notion of constructibility of Grothendieck?
Yes, yes. So here I should say that to be safe, I was a little careless here. I should, to be on the safe side, suppose S is Noetherian, and this is of finite type. This is the only case of interest for me. And then you have a good notion. In well, already constructibility on general schemes, you have to be a little careful. Yeah, what you mean by really closed. So then definition, we said that Fk is a psi good if our psi f, k, is in DBC. So for k in DBC, a constructible complex in the sense of Takeshi, of x cross s s lambda, and base change compatible. Actually, by theorem of Orgogozo, the second condition implies the first one. But here are some examples. If S is the dimension at most 1, then any Fk is a psi good. This is due to the limit. The case of dimension 0, by the way, is not trivial. This is a local acyclicity or mapped over a field. Second, if Fk is universally locally acyclic, then Fk is psi good actually, and in fact our phi f k is 0 universally. As Takeshi pointed out, this uses some argument in SGA 4.5 theorem finitude appendix. And 3, which was of use to him, suppose it's universally acyclic outside sigma in X, which is a quasi-finite over S. Then Fk is a psi good. And this implies the flatness of phi in his notation. So actually the bad cases are blow-ups or maps with hidden blow-ups like Saba constructed. But the main theorem is that after some modification, all losses are restored and Sorrow's end. That is, our psi becomes constructible and compatible with base change. So he had theorem of Orgogozo, which is that given so X over S, finite type, Noetherian here, and lambda, of course, is Z mod Ln, is model nu, and L is invertible on S. Then there exists a modification, let's say G from S prime to S, such that, well, S prime, K prime with the obvious notation that is base changed by G is psi F prime good. And this is the main result I will use in my proof of theorem 1. So now 4 is, I briefly describe the Cunes formula. Now suppose you have, so it's a very general situation. Suppose you have the situation x1 over y1 s y2 x2. So then you get x over y. This is the product x1 cross x2 over y over s. And if you have k1 here and k2 here, then by general nonsense you get a map from R psi f1 k1. So which lives on the vanishing topos of this map, tensor product of psi f2 k2 into psi f of k, where k is the external tensor product. And theorem 2 is that.
So if y is x1 to y1?
F1, F2, and F.
Yeah.
Is it okay?
Yeah, it's okay.
It's okay? Hmm? So theorem 2 is that assume F1, K1 psi good, Fi, Ki psi good. So this is always the case if if y is y1 and y2 are of dimension 1, which is the case of interest for me in the affine line. Then a star is an isomorphism, and in fact Fk is also psi good.
Do you assume that one of them is finite third dimension to make it bounded, or it's not?
So Ki, I'm sorry, Ki dCTF, yes. Thank you. Yes, thank you.
So So just to be sure to follow, so you are identifying the vanishing topos of F1, product vanishing topos of F2 with...
No. No, let me explain it here. So, or maybe because you're on the right-hand side here. So, in fact, you have here x1 goes to x1 cross y1, right? By psi f1. And then here you have x, and here x2, right? And here you have x cross y. You have two projections here. And here it's an x2 cross y2. So you have psi f and psi f2. And so what I said, saying that you have the map from the psi here, external tensor product here into the psi here, right? And I claim that if you assume that fi ki is psi good, then this map is an isomorphism, and also the R psi f. The fk is also psi good. And in fact, the proof is just a game using Orgogozo's theorem. In fact, the problem is that a priori you don't know whether this is a psi good. If it was, then it means that you could do base change and reduce to a tray. So if you reduce to a tray, then you are reduced to Gaber's theorem. So in fact, what you do is by Orgogozo, you make fk good by some proper hypercover. And then you have to use a cohomological descent. But then you have to use both classical cohomological descent, like in Deligne 50 years ago, and also a more recent cohomological descent, oriented descent by Gaber, which is also in this volume on his work. So then you get that. And then it's, I think, 5 minutes. Complicated, maybe I should. So in fact, it's then formal to deduce theorem 1 from theorem 2. So again, you use some general nonsense. So theorem 2 implies theorem 1. So suppose you have a composition like this. F, G, and GF. Then you have x to x cross y, and here you have x cross z. Here you have psi f, here you have psi gf. And here you have some map induced by G, which I denote by G with an arrow above. And of course, you have that R psi gf is Rg lower star of R psi f. So composition of vanishing cycle. So the effect of this G, so remember, suppose X is just a point. So what is this G with arrow? It's a projection of the minor ball at X to minor ball at Y. And somehow it's some kind of calculating direct image is calculating vanishing cycles. So vanishing cycles are vanishing cycles. And then you apply this to G equal to A, the sum map. And you get the formula. In fact, you get the formula first for R psi. That is R psi. R psi k is R psi k1, R psi k2. But you need the formula for R phi. So this is more complicated. So here you have to use two things. The sum map is locally acyclic. It's smooth, actually. So A is locally acyclic. And also you have to use some property of local convolution, namely that if you take something geometrically constant over your tray, and you start it with something extended by 0, something like this, so this is 0. So in fact, when you look at the nearby cycles for the vanishing cycles for the product map, F1 cross F2, then you have two components. You have the R phi tensor R phi, and you have an extra component, which is mixed. K1 tensor R phi 1 and R phi 1 tensor K2. It's like when you have two filtered objects of length 1 and take tensor product, you get the filtered object of length 2. So you have two parts, and you have to show that the R A lower star kills this remaining part, but this follows from this. So then you get the formula by looking at what happens at point, and you can even do that in families along the special fibers. So now, how do you recover Thom-Sebastiani, original Thom-Sebastiani? Then it's only on the tame case. So tame case, or maybe my time is almost finished, but tame case over K is K bar. Then star 1 is in fact tensor product, even for coefficients Z model n. For QL bar, there is a proof in some paper by Foulet using Fourier transform. But in any case, it's not difficult to see that by using the universal tame cover, the Kummer cover. And also, in this case, suppose you take G in I tame, Z prime hat of 1. So you have V1, V2, right? So if you look at D2 at V1 and D2 at eta bar, so then, of course, the monodromy acts on this talk and gives an automorphism. But as IT is commutative, this is an isomorphism, in fact, of the sheaf itself. So then you can view it as an automorphism of the sheaf. But when you take this, then you have some endomorphism of this also. And in fact, is that G upper star to this turns out to be G, let's say G1 upper star G2 upper star. So in other words, the action is the diagonal action obtained by G1 and G2 on the two components, and you can translate it into tensor product by this isomorphism. So you recover Thom-Sebastiani theorem. And with a little more work, you recover the variation morphism. But I have no time to talk about that. So thank you very much.
Question? Yes.
So, could you explain how precisely the star product appears? Because we stopped at the connect, so in the connect there is product, and in the application suddenly the star product appears.
Yes. So here you have this x1 cross x2 restricted to say A to H, and it goes to A2H and then to AH, and we have the sum map here. So now I get the R psi, let's say, R psi of K1, K2. So this is the external tensor product, my equivalent formula for F1, F2. And then how do I get the vanishing for this composition, AF, right? So I explained that you apply RA lower star. This will be the R psi GF, AF. So this is the RA lower star of this product here, R psi K1, R psi K2. Now take the stroke of this at some point. Look at the stroke of this at 0. So then, in fact, it will be the RA, I should write 0, 0 star of this R psi at 0, stroke at 0, tensor R psi at 0. And A00 is this, actually this localization here. So, in fact, this is just the definition of the tensor of the star product, right? This is by definition R psi star R psi. Except that here I work with the general K. In fact, I'm more interested in the R phi, and then in fact I have something on eta, and then I extend by 0, take some product, but this is basically the thing. So in fact, to understand the Stokes of this R psi, I should have said a little more, but I had no time. So in fact, in the local situation, it's a X, S, S. So then in this local situation, you have this psi to vanishing topos. And here the projection on SS. And here you have the localization of F. So this is the map from the small ball to the small ball. So this is a Milnor ball, Milnor ball. Now, by an observation due to Gaber, there is in fact a section of this map, sigma. And in fact, it has the property that sigma, so it depends on the point x. Sigma star of psi is just R psi star. So if you take R psi sigma star sigma star, nonsense. Sigma star of R psi here, that's a this is in fact the, so you take sigma star here or this, and then you get RF X S lower star.
You have arrow above the
Yeah, so sigma star is in fact here it's the second projection, and sigma star is P2 star. Yeah. So then you take pullback is the same as projecting, then you get that. Yeah. So this is the basic relation which enables you to understand the Stokes. So I should have said also that, but I'm taking too much time, but in fact, if you take in general, you have S here, maybe big dimension S, and T, point X. So what is the Stoke of R psi F, or let's say K, at a point, as I explained, X to S, and here a specialization map, like in Takeshi's expose. So this is, in fact, well, you would think first that it's just R gamma here of the xt, of the xs t, k, but this is not that actually. So the idea is that it is okay in dimension 1, but not in general. In general, you have to take a whole tube here. So it's slightly blurred. So you have here your spatialization map, you have S, and you have T, and the tube here is here. And this is a cohomology of Milnor tube. Yeah. In fact, what you get is R gamma of xs cross s t. Okay. And in the good case, psi good, then it commutes the cohomology of the tube restricts isomorphically to cohomology of the special fiber. So, in fact, you can. Somehow you have to think that this vanishing topos is a localization along S, and or along X if you prefer. And of course, here I just explained for just punctual isomorphism, but you can make it families on a whole special fiber. So you can define a global convolution, some global local convolution. So local downstairs, but global. And then you have a more general formula, and then you need that for the variation morphism, which is also tensor product proved by Deligne long ago, in fact. Okay, so I think I talked much too much. I'm sorry.
Can I ask one more
Yes.
question?
Oh,
So-
sure.
So you use the addition map.
Yes.
Yeah. What do you get with the multiplication map?
Very good question. So then, in fact, first of all, without essentially no change, you could get, let's say, for any group schemes, in fact, smooth group scheme, and a convolution at the origin. But you would be interested, for example, in convolution on GM, but at 0. So at 0, well, so at 0 you get something like this. Yeah. So already for the constant shift, you have vanishing cycles. So in fact, it can be analyzed, and you can look at the convolution, and you can look at the phi. There are two pieces, and you can analyze. But I've not gone very much there. But in fact. Local convolutions at various points of GM have been studied by, sorry, the name of the person now I don't remember, but more recently Wilson studied these local convolutions, several points of GM also, and also not just GM, but also for elliptic curves. So which is a very subtle example. But all of these somehow go into the frame of this general formalism, except that to calculate the local convolution is always hard, even for the additive convolution and even for the Artin-Schreier sheaf. I said in the tame case it's easy. Yeah, okay. But how about the wild case? Then by Lomont you have estimates on the rank and the swan. You have formulas for rank and the swan. But already Artin-Schreier is not, for example, take L psi. So what is it? So it's a rank 3 sheaf with swan 1. So 3 plus 1 is 4, which is 2 by 2, which is correct. But you have to to write it explicitly as a sum. Yeah. And so Wilson did that, and other more complicated examples also. Yeah. Okay.
Sure. So we thank the speaker again.
Thank you.